Hello everyone, this is Abhishek Mohanty and welcome to lecture number 8 of the chapter Electric Charge and Field. Students, in this lecture we will discuss about a very important topic, and the topic name is electric field lines or lines of force. So let's get started. So students, in the previous classes we had discussed about electric field. We know that whenever a charged particle or a charged body is placed at a point, then the space around the charge gets modified. Means an electric field is set up around a charged body, and this electric field is a vector quantity. It has magnitude and direction, and the strength of electric field is represented by a quantity, a vector quantity known as electric field intensity. And we had also discussed how to calculate the electric field intensity due to a point charge. Suppose a point charge Q is placed in vacuum, then the electric field intensity due to this point charge at a distance r from it is given by the formula E equal to 1 by 4 pi epsilon naught Q by r square. So by calculating the electric field intensity, we can find the strength of electric field at a given point. Now the question is, what is the meaning of electric field lines and what is its significance? Why should we know about electric field lines, or what informations can we get from the electric field lines? All those things will be covered in this lecture. So just look at the definition of electric field line. Electric field line may be defined as an imaginary curve along which a small positive charge would tend to move inside an electric field when free to do so. So we will discuss about the meaning of this definition. So first remember that electric field line does not really exist. It is an imaginary curve. It is an imaginary curve. Like the longitude, the latitude, they are imaginary curve. Similarly, the electric field lines are imaginary curves. They don't really exist. So what is the importance of these electric field lines, or what does it imply? So electric field line may be defined as an imaginary curve along which a small positive charge would tend to move inside an electric field when free to do so. Suppose in this region I have electric field. Suppose in this region I have electric field. Then how to draw the imaginary curves, or how to draw the electric field line? So to draw the electric field line, you have to do one thing: bring a small positive charge, and keep it inside the electric field. Keep the small positive charge inside the electric field and release it. So we know that every charged particle experiences force inside the electric field. So if you bring a small positive charge and place it at any point inside the electric field, then that small positive charge will experience a force, and when it will experience a force, it will be accelerated. According to Newton's second law of motion, whenever a net force acts on a body, there will be acceleration. So if you place a small positive charge inside the electric field, it will be accelerated and it will start moving due to the electrostatic force acting on it. And when it will move inside the electric field, you have to just look at the path followed by the charged particle, along which path it is moving. Then draw that path. That path will be the electric field line. Do you understand? Again I am repeating. Electric field line may be defined as an imaginary curve along which a small positive charge would tend to move inside an electric field when free to do so. So you have to first bring a small positive charge and place it inside an electric field and look at the path followed by the small positive charge, and if you can draw that path will represent the electric field line. Is that clear? And remember that this electric field line may be a straight line or may be a curved line. Electric field lines, in some cases it is a straight line, in some cases it is a curved line. And to draw the electric field, you have to draw the path followed by a small positive charge. Remember this important point. Whenever you are drawing the electric field line or electric lines of force, you have to look at the path followed by a small positive charge. Don't look at the path followed by a negative charge. Look at the path followed by a small positive charge. Is that clear? So with more examples, we can understand how to draw the electric field lines in various cases. So we know that electric field can be created by many kind of charged particles. So the simplest electric field is created by a point charge. Now let us draw the electric field line due to a point charge. Suppose I will bring a positive point charge plus Q and I will place it at this point. Suppose a positive point charge plus Q is placed at this point. Then it will create an electric field around itself. Now we have to draw the electric field line due to this positive point charge. So how to draw it? Look at this process. You have to bring a small positive charge, or you can say you have to bring a test charge, because we know that test charge is always positive and its magnitude is very small as compared to the source charge. So now I will bring a test charge Q0 and I will place that test charge at any point inside the electric field. The electric field is spread throughout the region. So I will bring a test charge and I will place it at any point inside the electric field. And then I will look at the path followed by the test charge. Suppose I will bring a test charge Q0 and place that test charge here. Suppose I will bring a test charge Q0 and place that test charge at this point. Then what will happen? The source charge is positive and here the test charge is also positive. So you will see that this test charge will experience a repulsive force. This test charge will experience a repulsive force due to the source charge. And we know that the Coulomb's force is a central force, means the Coulomb's force acts along the line joining the two charges. So if you join the two charges with a line, then the repulsive force will act along this line, and due to this repulsive force the test charge Q0 will move away from the source charge. So this is the trajectory, or this is the path followed by the test charge. So this is the electric field line. Similarly, if you want, you can place the test charge at this point. So when the test charge is placed at this point, then the force will act along this line and hence the test charge would move along this direction. Similarly, if you place the test charge here, then the force will be along this direction. So the test charge will move along this direction. Similarly, by placing the test charge at different points, you can draw the electric field lines at different directions. So these are the electric field lines due to a positive point charge. The electric field lines due to a positive point charge. And you can see that the electric field lines are radially outward. This charge plus Q is at the center and the electric field lines are emerging out of this positive point charge. Is that clear? So in this way you can draw the electric field line due to a positive point charge. Now let us draw the electric field line due to a negative point charge. Suppose we have a single negative charge and we have to draw the electric field line due to this negative charge. Then how to draw it? Again the same process, bring a small positive charge or bring a test charge and place that test charge inside the electric field and look at the path followed by the test charge. That path will represent the electric field line. So if I place the test charge Q0 somewhere here, then the test charge is positive charge, test charge is always positive, and here the source charge is negative. So if you place test charge here, it will be attracted towards the source charge. means the test charge will move towards the source charge. That's why the arrow mark will be towards the negative charge. In the first case, the test charge was moving away from the source charge, that's why the arrow mark was outward. But here, if you place a test charge, then the test charge will experience an attractive force due to this negative point charge, and that's why it will be attracted towards the negative charge, and that's why I have given a inward arrow mark. Similarly, if you place test charge here, it will experience a force in this direction. Okay, so in this way you can draw many electric field lines due to this negative point charge. So this is known as radially outward field lines, radially outward field lines, and this is known as radially inward field lines, radially inward field lines. Radially outward and radially inward means what? If you look at the diagram here, you can see that the charge particle or the point charge is at the center, and the electric field lines, they are emerging out of the point charge, or the electric field lines are entering to the point charge. If it is negative charge, then the electric field lines will enter to the point charge, and if the charge is positive, the electric field lines will emerge out of the point charge. So this is known as radially outward field line, and this is known as the radially inward field line. So remember that the electric field line always originates or always starts from a positive charge body and it ends on a negative charge body, because when we are defining the electric field line, we are looking at the path of the small positive charge. So if you will take a positive charge body and you want to study or you want to draw the electric field line due to the positive charge body, then this small positive charge will definitely go away from the positive charge body, and that's why the electric field line will always be outward for a positive charge and it will be inward for a negative charge. So now we will discuss some important points about the electric field line. So remember that electric field lines always start from positively charged body and end on negatively charged body. This is the first point you have to remember. The electric field lines always start from positively charged body and they end on negatively charged body. In no cases you will see that electric field line is starting from negative charged body and ending on positive charged body. That is impossible. Electric field lines always start from positive charged body and they end on negatively charged body. So if we have only positive charged body, if there are positive and negative charged body, then obviously it will start from positive and end on negative. But if we have only positive charged body, means in the absence of a negatively charged body, what will happen? The electric field line will start from the positive charged body and they will end at infinity. Remember that in the absence of negatively charged body, electric field lines end at infinity. तामाने जदि आम पाखे गोटे पॉजिटिव चार्ज बॉडी अच्छी आ गोटे नेगेटिव चार्ज बॉडी अच्छी, then definitely electric field line will start from positive and end on negative. But जदि आम पाखे only positive charge body अच्छी and there is no negative charge body, then in that case what will happen? The electric field line will start from positive charge body and end at infinity. Is that clear? Similarly, what will happen if we have only negative charge body, there is no positive charge body? ताहले कौन हबो? So in the absence of positively charged body, what will happen? तो फर्स्ट केस रे आमे कौन डिस्कस कले, जदि हम पाखरे पॉजिटिव एंड नेगेटिव बोथ टाइप रो बॉडी अछंती, देन द इलेक्ट्रिक फील्ड लाइन्स विल स्टार्ट फ्रॉम पॉजिटिव चार्ज बॉडी एंड एंड ऑन नेगेटिव चार्ज बॉडी. सेकंड केस आमे कौन डिस्कस कले, जदि हम पाखरे केवल पॉजिटिव चार्ज बॉडी अछि एंड द नेगेटिव चार्ज बॉडी इज एब्सेंट, तो से केस रे कौन हबो ना, इन द एब्सेंस ऑफ नेगेटिवली चार्ज बॉडी इलेक्ट्रिक फील्ड लाइन्स एंड एट इंफिनिटी. The third case is, if we don't have any positive charge body, we only have a negative charge body, तो सही केस रे कौन हबो, तो इलेक्ट्रिक फील्ड लाइन डेफिनेटली एंड हबो एट नेगेटिव चार्ज बॉडी, बट स्टार्ट कुड हबो, इट विल स्टार्ट फ्रॉम इंफिनिटी. इन द एब्सेंस ऑफ पॉजिटिवली चार्ज बॉडी इलेक्ट्रिक फील्ड लाइन्स start from infinity. So remember these three important points. So the electric field lines always start from positively charged body and end on negatively charged body. This is the first point. In the absence of negatively charged body, electric field lines end at infinity. This is the second point. And the third point is, in the absence of positively charged body, the electric field lines start from infinity. Is that clear? तो आम से ऑलरेडी फिगर ड्रॉ कर देचे. जदि हम पाखरे गोटे सिंगल पॉजिटिव चार्ज अच्छी, देन द इलेक्ट्रिक फील्ड लाइन्स विल बी रेडियली आउटवर्ड लाइक दिस. द इलेक्ट्रिक फील्ड लाइन्स विल बी रेडियली आउटवर्ड. And you can see that here we have only positive charge body, there is no negative charge body. तो एक केस रे कोन होची, द इलेक्ट्रिक फील्ड लाइन्स दे आर ओरिजिनेटिंग और दे आर स्टार्टिंग फ्रॉम दिस पॉजिटिव चार्ज बॉडी एंड दे आर एंडिंग एट इंफिनिटी. इज दैट क्लियर? सिमिलरली इफ यू हैव ए सिंगल नेगेटिव चार्ज, तो से केस रे इलेक्ट्रिक फील्ड लाइन्स केमती आसीबो, रेडियली इनवर्ड. द इलेक्ट्रिक फील्ड लाइन्स विल बी रेडियली इनवर्ड. You can see that the electric field lines are ending on the negative charge body, but what is their starting point? They are originating from infinity. So in the absence of positively charged body, the electric field lines start from infinity. So here we cannot see from what point are they originating or are they starting. So I am कहि परिबा जे the electric field line are starting from infinity. Is that clear? The next important point is that electric field lines are continuous curve. Electric field lines are continuous curve without any sudden break. Break. So this is a very important point. The point is, electric field lines are continuous curve. The continuous curve रे meaning कौन? So electric field lines are continuous curves without any sudden break. ता माने कौन से भी चार्ज डिस्ट्रीब्यूशन पाई इलेक्ट्रिक फील्ड डिसकंटिन्यूअस हबो नहीं. ता माने जदि मु गोटे फिगर ड्रॉ करिबी लाइक दिस, then this type of electric field line does not exist. कहेंगे ना electric field line रा meaning कौन ना, it is the path along which a unit positive charge or a small positive charge or a test charge will move inside an electric field when it is free to do so. तो charge particle गोटे electric field भितरे continuous force experience करिवो. Is that clear? Whenever we have electric field, a charged particle, a test charge inside the electric field will experience a continuous force. And since the charged particle will experience a continuous force, the electric field line will also be continuous. ता माने जो region रे electric field थिबो, से region रे गोटे charged particle उपरे force आसीबो and the force will be continuous. Inside electric field, at no point force can be zero. Is that clear? So if the force is continuous, then the electric field lines will also be continuous. जदि आमे किछि ब्रेक करिबा, जदि आमे इलेक्ट्रिक फील्ड लाइन रे किछि ब्रेक करिबा, तार मीनिंग कोन हबो? तार मीनिंग हबो इन दिस रीजन there is no force acting on the charge particle, acting on the small positive charge or test charge. But this is impossible. जदि गोटे रीजन रे इलेक्ट्रिक फील्ड अछि, then definitely से रीजन रे गोटे चार्ज पार्टिकल फोर्स एक्सपीरियंस करिवो, and the force is continuous. It cannot have any break. तो जदि हम किछि ब्रेक प्रोड्यूस करिबा इलेक्ट्रिक फील्ड लाइन रे, तार मीनिंग कोन हे जिवो? तार मीनिंग हे जिवो जे ए रीजन रे देयर इज नो इलेक्ट्रिक फोर्स ऑन द टेस्ट चार्ज. But this is impossible. A test charge always experiences force inside an electric field. So remember this point, that electric field lines are continuous curves without any sudden break. Now we will discuss the next point, very important point. So electric field line ro आउ गोटे important significance कोन? Suppose this is the electric field line. एमती गोटे electric field line अछि. I had told you that electric field lines may be straight lines or may be a curved line. Suppose in a given region this is the electric field line. तो electric field line को देखला परे how can we determine the direction of electric field intensity at a given point? Suppose I will ask you to find the direction of electric field intensity at this point. Okay, how to find it? So the point is the tangent drawn to an electric field line at a given point represents the direction of electric field intensity at that point. The tangent drawn to an electric field line at a given point represents the direction of electric field intensity at that point. तामाने जदि आमे wish करूचे to find the electric field intensity direction at this point, what we have to do? Just draw a tangent to the electric field line at that point. आमे कौन करिबा? आमे से given point रे गोटे tangent draw करिबा to the electric field line. So let me draw a tangent here. So this tangent will represent the direction of electric field intensity at this point. Electric field intensity ro direction at this point will be along this tangent. And if electric field intensity is directed along this tangent, it means the electrostatic force acting on the test charge will also be directed along the same direction, because we know that F vector equal to Q naught into E vector. Q naught is a positive charge particle. So the direction of electrostatic force is same as the direction of electric field if we have a positive charge. Okay, तामाने जेहेतु A point रे electric field intensity direction is along this tangent, it means the electrostatic force direction is also along the tangent. Or we can say that this tangent represents the direction of acceleration on the test charge, because the direction of acceleration is same as the direction of the force. So this tangent will represent the direction of electric field, the direction of force on a positive charge, and the direction of the acceleration of the positive charge or of the test charge. Is that clear? So based on this concept, we will discuss about the next point. The next point is that two electric field lines two electric field lines never intersect each other. Never intersect each other. Two electric field lines never intersect each other. Tamane, suppose this is one field line, this is other field line, they can never intersect each other. Tamane, this diagram is wrong. This type of diagram is wrong. Two electric field lines, they can never intersect each other. What is the reason behind it? Suppose the two field lines intersect. Suppose they intersect kale. Then look at the point of intersection. Look at the point of intersection. So ame ei jo point ame kon padhile? Now the tangent drawn to an electric field line at a given point represents the direction of electric field intensity at that point. Okay. So this point of intersection is common to both the electric field lines. Tamane, this point lies on this field line and this point also lies on this field line. So jodi mu ebe kon karibi, tangent draw karibi. I will draw the first tangent to this curve, the second tangent to this curve. So I will get two tangents. I will get two tangents. And the tangent represents the direction of electric field intensity. Tamane, at a single point, I can draw two tangents to the two electric field lines. And the two tangents will represent two different directions of electric field intensity. But this is not possible. Gote single point re electric field ro two directions is not possible. So electric field lines never intersect each other. Jodi se mane intersect karibe, then gote single point re ame duita electric field ro direction paiba, which is not possible. That's why electric field lines never intersect each other. This is the very important point. Next point is that electric field lines never form closed loop. Electric field lines never form closed loop. What is the reason behind it? Electric field lines never form closed loop. Suppose we have a positive charge body here and we have a negative charge body here. Okay, we have a positively charged body and a negatively charged body. So I already draw kari sariche the electric field lines due to a single positive charge, means radially outward, and electric field lines due to a single negative charge, means radially inward. Suppose we have a positive charge and a negative charge. We have a system of positive and negative charge. So ei case re electric field line kemti asibo? Let us discuss about that. So electric field line ko draw kariya pai, what is the method? Bring a test charge, place at any point inside the electric field and look at the path. So ei case re jodi am pakhare positive charge achi au negative charge achi, to kon habo? Ei case re electric field line ra shape kemti asibo? Let us bring a test charge Q0 and place here. So ebe kon habo? This test charge will be repelled by this positive charge, but this test charge will be attracted by the negative charge. Is that clear? Jodi negative charge absent thibo, then the test charge will experience only repulsive force. So se gote straight line re move karibo because Coulomb's force central force. Kintu jodi gote negative charge achi, mane positive or negative both achanti, tabe kon habo? This test charge will experience two forces: repulsive force due to the positive charge, attractive force due to the negative charge. Repulsive force will be along this direction, attractive force will be along this direction. So the resultant force will be along this direction. Tamane charge particle ta, the charge particle, the test charge will neither move along this line nor move along this line. See gote resultant फोर्स रो डायरेक्शन रे से मूव करिवो। तो आम यह कहि परिबा जे इफ वी हैव a system of two charges, one positive and the other negative charge, then the test charge will move away from the positive charge and move towards the negative charge. तो सही केस रे इलेक्ट्रिक फील्ड लाइन रो पाथ केमते आसीबो लाइक दिस, द इलेक्ट्रिक फील्ड लाइन विल बी लाइक दिस. सो जदि एग्जाम रे क्वेश्चन आसीबो ड्रॉ द इलेक्ट्रिक फील्ड लाइन ड्यू टू टू ऑपोजिट चार्जेस or due to a dipole. आपको मैं dipole भी कहि परिबा, and what is dipole we will discuss it in the next class. So dipole बा हमें कहि परिबा opposite charges. Opposite charge system पाई electric field line केमते आसीबो, this is the shape. The test charge will move away from positive charge and towards negative charge, and you can say that the arrow mark is away from positive towards negative. तार अर्थ कोन, test charge टा positive charge रु away जिवो और नेगेटिव चार्ज रो टुवर्ड्स जीवो. इज दैट क्लियर? ओके. सो ए जो पॉइंट लिखा है इलेक्ट्रिक फील्ड लाइन्स नेवर फॉर्म क्लोज लूप, तार माने कोन, जदि गोटे फिगर रे इलेक्ट्रिक फील्ड लाइन को एमती फिगर रे रिप्रेजेंट करा है, देन दिस टाइप ऑफ इलेक्ट्रिक फील्ड लाइन डज नॉट एग्जिस्ट. दिस टाइप ऑफ इलेक्ट्रिक फील्ड लाइन डज नॉट एग्जिस्ट, नॉट पॉसिबल. काहे कि देखो एटा गोटे क्लोज लूप, तो एमिति इलेक्ट्रिक फील्ड लाइन इम्पॉसिबल. व्हाट इज द रीजन बिहाइंड इट? तो सपोज आमे एठी गोटे पॉजिटिव चार्ज प्लेस करिबा, एठी गोटे नेगेटिव चार्ज प्लेस करिबा. आमे जानिचे इलेक्ट्रिक फील्ड लाइन ऑलवेज स्टार्ट फ्रॉम पॉजिटिव चार्ज बॉडी एंड एंड ऑन नेगेटिव चार्ज बॉडी. तो लुक एट द अपर पार्ट, एठी कोन होची इलेक्ट्रिक फील्ड लाइन टा पॉजिटिव रे बाहरला, नेगेटिव रे एंड हला. तो जदि से गोटे क्लोज लूप फॉर्म करिवो, देन लोअर पार्ट रे कोन हबो, इलेक्ट्रिक फील्ड लाइन टा नेगेटिव रु स्टार्ट हे कि पॉजिटिव रे एंड हबो. बट दिस इज नॉट पॉसिबल अकॉर्डिंग टू द डेफिनेशन ऑफ इलेक्ट्रिक फील्ड लाइन. इट इज नॉट पॉसिबल. इलेक्ट्रिक फील्ड लाइन ऑलवेज स्टार्ट फ्रॉम पॉजिटिव एंड एंड ऑन नेगेटिव. ता माने जदि एमिति फिगर थिबो एटा होचे रॉन्ग फिगर, दिस इज द करेक्ट फिगर. देखो ए फिगर कोन अछि, द इलेक्ट्रिक फील्ड लाइन टा पॉजिटिव बाहरला, नेगेटिव रे एंड हला अपर पार्ट रे, लोअर पार्ट रे मध्य से सेम केस पॉजिटिव रे बाहर की नेगेटिव रे एंड हला. त माने इलेक्ट्रिक फील्ड लाइन टा ए नेगेटिव चार्ज रे एंट्री करी कि एपटे बाहर की पॉजिटिव रे एंड हे परिबो नाही, बा इलेक्ट्रिक फील्ड लाइन केबे भी गोटे क्लोज लूप फॉर्म करिबो नाही. किंतु गोटे मैग्नेटिक फील्ड लाइन क्लोज लूप फॉर्म करि परिबो. आमे पढिचे क्लास 10th रे, जदि आमे गोटे बार मैग्नेट नबा, इफ वी टेक ए बार मैग्नेट and this is the north pole, this is the south pole, the magnetic field lines are directed from north to south outside the magnet, but inside the magnet it is directed from south to north. ता माने magnetic field lines they will form closed loop, but electric field lines will never form closed loop. So these are some of the important points of electric field lines. So आमे ड्रॉ कले इलेक्ट्रिक फील्ड लाइन्स ड्यू टू ए सिंगल पॉजिटिव चार्ज, ड्यू टू ए सिंगल नेगेटिव चार्ज, ड्यू टू ए पेयर ऑफ ऑपोजिट चार्जेस. वी हैव ए पॉजिटिव चार्ज, नेगेटिव चार्ज. तो एबे हमें कोन देखुचे ना, जदि गोटे सिंगल पॉजिटिव चार्ज थिला, इलेक्ट्रिक फील्ड लाइन टा रेडियली आउटवर्ड मूव करथला. किंतु जदि मैं कोन करिवि, ए पॉजिटिव चार्ज पाखरे गोटे नेगेटिव चार्ज प्लेस करिवि, एबे कोन हबो, this electric lines of force or this electric field line will contract. This electric field line will contract. आको में कहिबा longitudinal contraction or lengthwise contraction. A contraction रो significance कौन, a contraction रो importance कौन ना, this contraction represents the attractive force between two unlike charges. There is an attractive force between two unlike charges, and that attractive force is given by the contraction of the electric field line. Similarly, if we have two like charges, suppose दुईटा like charge अछि, तबे देखो suppose जदि गोटे सिंगल पॉजिटिव चार्ज थिबो, तो इलेक्ट्रिक फील्ड लाइन केमती आसीबो, रेडियली आउटवर्ड आसीबो लाइक दिस. बट जदि मुझे कौन करी गोटे सेकेंड पॉजिटिव चार्ज प्लेस करदेवी दिस टू आर लाइक चार्जेस तो ये कौन हम ये जो पॉजिटिव चार्ज पे इलेक्ट्रिक फील्ड लाइन आसीबो तो ये कौन हम देयर विल बी रिपल्सन बिटवीन द टू इलेक्ट्रिक फील्ड लाइन्स तो वर्तमान इलेक्ट्रिक फील्ड लाइन टा केमती हो जिवो लाइक दिस दे विल रिपेल ईच अदर आक में कहबा लैटरल रिपल्सन विल कॉल इट एज लैटरल रिपल्सन इज दैट क्लियर ता माने इलेक्ट्रिक फील्ड लाइन दे मे कंट्रैक्ट अगेन मु फिर आते ड्रा करूची जदि गोटे सिंगल पॉजिटिव थिबो इलेक्ट्रिक फील्ड लाइन आसीबो रेडियल आउटवर्ड लाइक दिस जदि सिंगल नेगेटिव थिबो द इलेक्ट्रिक फील्ड लाइन विल बी लाइक दिस रेडियल इनवर्ड किंतु जदि मुझे कौन करी गोटे नेगेटिव ये प्लेस करदेवी तबे कौन हम इलेक्ट्रिक फील्ड लाइन रो शेप चेंज हो द शेप ऑफ इलेक्ट्रिक फील्ड लाइन विल चेंज इज दैट क्लियर द शेप ऑफ द इलेक्ट्रिक फील्ड लाइन विल चेंज आपको मैं कहबा लेंथ वाइज contraction and this contraction represents the attractive force between the unlike charges and this repulsion this lateral repulsion represents what the repulsive force between two like charges is that clear so the next point is the relative closeness of electric field lines the relative closeness of electric field lines indicates the strength of electric field तमाने रिलेटिव क्लोजनेस रो मीनिंग कौन द गैप बिटवीन द इलेक्ट्रिक फील्ड लाइन्स तमाने जदि इलेक्ट्रिक फील्ड लाइन्स आर वेरी क्लोज टू ईच अदर then in that region the electric field is very strong and if the gap between the electric field lines is large or the electric field lines are far apart from each other then in that case the electric field will be weak for example जब मैं एमती फिगर ड्रॉ करूची then you can see that the distance between or the gap between electric field lines is less in this region but if you look at the left side the gap between electric field lines is large or we can say that the electric field lines are more close to each other at this end tamane this region has a strong electric field and this region has a weak electric field the relative closeness of electric field lines indicates the strength of electric field if the separation between the electric field lines is less then the electric field is strong and if the separation is large then the electric field is weak is that clear and if we have a uniform electric field then how to represent uniform electric field using field line so uniform electric field means at every point the magnitude and direction of electric field intensity are same तो यूनिफॉर्म इलेक्ट्रिक फील्ड को आमे केमिति शो करेबा इज रिप्रेजेंटेड बाय यूनिफॉर्म इलेक्ट्रिक फील्ड इज रिप्रेजेंटेड बाय parallel and equispaced field lines like this parallel meaning kon parallel means the direction is same at every point and equispaced means the magnitude of electric field is same at every point okay again I am repeating if you have uniform electric field in a region then how to represent it by using the electric field lines by drawing parallel and equispaced So since the electric field lines are parallel, it means the direction of electric field intensity is same everywhere, and the equal spacing between the electric field lines indicates the same strength or same magnitude of electric field intensity at every point. This is known as the uniform electric field. Another important point is the electric field lines are always perpendicular. Electric field lines are always perpendicular to the surface of a conductor, to the surface of a conductor in which the charges are in equilibrium, where the charges are in equilibrium. Electric field lines are always perpendicular to the surface of a conductor in which the charges are in equilibrium. तार मीनिंग कौन? जदि गोटे कंडक्टर रे किछि करंट फ्लो होनी, इट मीन्स there is no net force on the charge particle. Charge particle means basically the free electrons. तो जदि गोटे कंडक्टर रे किछि करंट फ्लो होनी, means the charges are under equilibrium. तो से केस रे कोन हबो? Electric field lines are always perpendicular to the surface of the conductor. जदि से surface रे जदि से कंडक्टर करंट फ्लो होथबो, then this point is not valid, because when current flows through a conductor, then the electrons experience some force and they flow from one end to the other end. But this point is valid only when the charges are in equilibrium, means there is no current flowing through the conductor. तो से केस रे कोन हबो ना, the electric field lines are always perpendicular to the surface. What is the reason of it? Suppose this is a conducting surface. So this point states that electric field lines must be normal or must be perpendicular to this surface. Suppose assume that the electric field line is not perpendicular to the surface, rather it makes some angle theta. This theta is not 90 degree. तो जदि इलेक्ट्रिक फील्ड लाइन सरफेस को परपेंडिकुलर न हुए, देन कौन हम? We have some component of electric field along the surface of the conductor. If you resolve electric field E vector, you will get two components, E cos theta along the surface and E sin theta perpendicular to the surface. You will get two components, E cos theta along the surface and E sin theta perpendicular to the surface. Since we have a component of electric field along the surface, due to this component of electric field, the charge carriers, the free electrons on the surface will experience a force. आमे जानिचे गोटे charge particle will experience a force inside electric field. जदि electric field रो किछि component रहिबो along the surface, then due to this component the free electrons will experience some force. But we are talking about the charges in equilibrium. Charges in equilibrium means there is no net force on the charge particle. So जदि charge माने equilibrium में थिबे, then there should be no component of electric field along the surface. ता माने E cos theta component, it should be 0. Equilibrium condition पाई E cos theta should be 0. जदि E cos theta 0 न होबो, then the charges will experience some force and their equilibrium condition will not be achieved. So E cos theta must be 0. If E cos theta equal to 0, that implies cos theta equal to 0 and that implies theta equal to 90 degree. ता माने electric field lines must be perpendicular to the surface of a conductor in which the charges are in equilibrium. So students, these are some of the important points related to the electric field lines and electric lines of force. Hopefully you have understood what is the meaning of electric field line or electric lines of force, what is their significance, and how to draw electric field lines for various charge distribution. So in the next class we will discuss about another very important topic known as electric dipole, and there we will discuss about how to calculate electric field due to the dipole. So till then, bye bye and have a nice day.